Welcome to the lecture on characteristics of turbulent flow. So, we will have a few more aspects about the turbulent flow and then how we start modeling what are the approaches towards modeling some of the parameters in turbulent flow. So, that we will study in this lecture. So, we will talk about initially some of the examples of the turbulent flows, and especially with the constant imposed pressure there will be some kind of flow which is coming under the these examples, like you have free turbulent flow. So, you will have the example of mixing layer or jet or wake. So, these are the examples of free turbulent flows, whereas if you talk about the boundary layers near the solid walls. So, in that you may have the flat plate boundary layer or the pipe flow. So, they are basically coming under the boundary layer near the solid walls. So, if you see the free turbulent flow, so in that case you will have three kind of flows. So, if you talk about the mixing layer, so the in the mixing layer, basically a mixing layer will be forming the interface of two regions, one with fast and one with the slow moving fluid. So, that is how the mixing layer is defined. So, you will have the interaction between the fast and the slow moving fluid. Similarly, when you talk about a jet region, so there you have a high speed flow. So, you are leaving a jet, so that has high speed flow, and then when it goes, so it will be surrounded by the stationary fluid. So, then how how it behaves, how the there is interaction from the surrounding stationary fluid of the high speed flow. So, that is also an example of the free turbulent flow. Then also there is a wake kind of situation where it is formed behind an object in a flow. So, here we will have a slow region, moving region, and that will be surrounded by the fast moving fluid. So, the fast moving fluid is there, and there is a behind the object you will have that interaction which is there in the case of the wake. So, these are the examples of the some of the examples, and we will talk about few of them, and then we will talk about how the velocity profile, or how you are going to have the calculation of the stresses and all that. So, that we will be discussing. So, so initially, so in these cases velocity changes which take place in the initial thin layer. So, that becomes very important in all these three flows, and then you will have the transition to turbulence will be occurring after a very short distance in the flow direction from the point where the different streams basically will be initially meeting, and turbulence will be causing the vigorous mixing of adjacent fluid layers and rapid widening of the region across which velocity changes take place. So, that can be understood by the example of these three kind of flows. So, that is normally for the case of jet flow, where you see that you have a very high speed jet which is coming, and it has the interaction with the stationary fluid. So, you will have a stationary on the sides, and that is how the velocity profile come out to be. Now, in the case of mixing layer, you will have a smaller moving slow moving region, and that will be interacting with the fast moving one. So, that way you have mixing layer and development of these velocity profile you will see. Similarly, this is the wake. So, you will have a wake, and in that when it there will be velocity. So, that way what you see, that this is how the change in the velocity profile looks like. So, these are the examples of the free turbulent flows. Now, when we talk about the experimental observations of the turbulent flows, then what has happened that these for the for mixing layers. So, you will have these are the equations which describe the mixing layers, like you have u minus u min upon u max minus u min, that will be function of y by b. So, basically the u max and u min, they will be representing the maximum and minimum velocities. So, that will be at a distance y. So, that will be or at a distance x downstream. So, accordingly you will have the u by u max. So, so that you can see u by u max for the jets, it will be a function of y by b. Similarly, you will have so this y is the distance in the cross stream direction, and x is the distance in the stream, in that stream direction. So, you will have the u by u max, it will be function of y by b. Similarly, in this case u minus u min by u max minus u min, that will be for as b a function of y by b. So, that will be y in the cross stream, and then you will have similarly you will have for the and b is basically the cross stream layer width. So, that is half width. So, that is how b you are taking, and for the wakes, what you see, that this you see u max minus u by u max minus u min. So, that will be a function of y by b. So, that is what is these formulas are there, which talk about these variations in the u with u max u min, and it will be a function of how it is for the y by b. Now, if you go for the boundary layer near the solid walls. So, if suppose we are taking the case of boundary layer near the solid walls. So, in the turbulent thin shear layer flows, this Reynolds number based on length scale L and in flow direction, that is REL, is always very large. So, if you are taking that length scale L, and if you are measuring that turbulence value, this Reynolds number value, that will be always very large, and that implies, or that means that the flow is very much inertia dominated. So, that is what it means, that the flow is when the Reynolds number is very large, and we know that Reynolds number will be more than I mean this is a ratio of the inertia to the viscous forces. So, basically you will have a very large value of Reynolds number, means that your Reynolds number is, I mean, inertia force is dominating over the viscous force. Now, if you talk about the inertia forces, so that will be happening when your the flow is far away from the wall. So, there you will have this thing taking place. In flows along the solid boundaries, there is usually a substantial region of inertia dominated flow far away from the wall, and a thin layer within which the viscous forces are important. So, you have basically a very thin layer where the viscous forces are important, and once you go to the region which is far away from the wall, there the inertia force I mean tries to be more important or more dominant than the viscous force. Now, if you talk about the close to the wall, the flow will be influenced by the viscous effects and does not depend on the free stream parameters, and the mean flow velocity will be only depending on the distance y from the wall, fluid density rho, and viscosity mu, and the wall shear stress tau w. So, this point I mean that can be represented by, like if you are talking about this case, like where the at the distance y you will have this close to the wall, it will be depending upon. So, in that case your u will be a function of the distance from the wall, then your density, viscosity and the tau w. Now, this tau w is the wall shear stress in this case. So, this is basically for the close to the wall, and when you do the dimensional analysis in this case, then what you see is that the dimensional analysis will show that you get u plus, that will be equal to u by u tau. So, u tau is the known as the friction velocity. So, and that will be basically square root of tau w by rho. Now, that will be basically a function of rho u tau y upon mu. So, this way you get another number, I mean another parameter. So, that is rho u tau y by mu, and that is also known as f of y plus. So, this y plus this is simply y plus. So, this y plus will have certain values, and certainly on the wall y is 0. So, it will be 0, and as you move from the wall, y plus value will go on increasing. So, this formula u plus will be f f of y plus, that is u by u tau. So, this equation is known as the law of the wall. So, you will have two important dimensionless groups, one is u plus, another is y plus. So, so that way, and this u plus is basically defined as u tau, that is u tau is defined as tau w by rho raised to the power half. So, this is basically the friction velocity tau w, u tau is known as, and tau w is the wall shear stress and rho is the density. So, so that is how you will have the two dimensional groups you are getting in this case. Now, when you go away from the wall, now in that case so if you go away from the wall, the velocity at a point they can be considered to be influenced by the retarding effect of the wall through the value of the wall shear stress, but not by viscosity itself. So, as we move so far away from the wall, so there basically you will have the influence of the wall shear stress, not because of the viscosity itself. So, the length scale in this region will be the boundary layer thickness, that is delta. So, in that case, when you move far away from the wall, now in that case your u becomes another function g of the y delta rho and tau w. So, you will have the y cross stream length, you will have the boundary layer thickness, you will have the density and also the wall shear stress. That is what is normally there when you are moving away from the wall. So, in this case if you do the dimensional analysis, you get again u plus, that will be again u by u tau, that is your friction velocity, and that becomes g of y by delta. So, this this is the most useful form which you get, and the wall shear stress basically what we seen as the cause for the velocity deficit, that is u max minus u, and it will be decreasing. So, as you go towards the boundary layer edge, so at the pipe center line. So, what we see in this case u max minus u, so that will be and divided by u tau. So, that becomes the function of g of y by delta. So, that is what we had seen earlier also in those cases, that you get such kind of relationship there. So, this what you get, this is basically known as the velocity defect law. So, we are getting the velocity deficit in that case, and that is why we call it as the velocity defect law. Now, we move to the linear or viscous sublayer. Now, that has to be for the linear or viscous sublayer. So, if you go to the linear or viscous sublayer, so in that basically the fluid layer is in contact with a smooth wall. So, if you talk about that linear or viscous sublayer where the fluid layer is in contact with the smooth wall, it means since the wall is stationary, so the fluid which is there, that is also stationary. Now, the turbulent eddying motions which are there, so close to that will also be stopping, and you will have so you will have the domination by the viscous effects there in that condition. Now, the viscous sublayer which is there, so that basically is very thin. So, this viscous sublayer, so being very thin, it is basically confined to y plus value less than 5. And it can be assumed there that the shear stress, so shear stress will be constant approximately. So, shear stress is assumed to be constant and equal to the wall shear stress tau w throughout the layer. So, in that layer, as the layer is very thin, you can assume that the shear stress will be tau w, that is constant throughout that layer. So, tau y will be mu of dou u by dou y, and that will be tau w. So, that is what there in the case of a linear or viscous sublayer. Now, if you do the integration of this and if you apply the proper boundary condition, the boundary condition will be that if at y equal to 0, u is 0. So, in this case what we see, we get a linear relationship, and after integrating what we get is u equal to tau w into y upon mu. So, that is what you get from here. Once you get the integration constant, then that so putting the boundary condition, you get this value u equal to tau w y by mu. So, you can have the further you can what you see earlier, you have got the u by u tau is u plus, and y plus also you see that is rho u tau y by mu. So, you can write here from u by u y, u by u tau and all that. So, you can write here. So, with some algebra you can further define u plus and y plus, and you get the u plus as equal to y plus. So, this you have a linear relationship here between the u plus and the y plus. So, that is between the velocity and the distance from the wall, and that is in the fluid layer which is adjacent to the wall. So, this is a linear sublayer, that is why it is known as the linear sublayer, because you have the linear relationship between u plus and y plus, and that is why it is known as linear sublayer. Now, if you go to the outside this viscous sublayer. So, you have a log law layer. So, that is basically the turbulent region close to smooth wall. Now, if you go to this region, where now in this region will be basically by a region where the y plus value will be more than 30 and less than 500. So, here this is outside the viscous sublayer. So, in that region your y plus will be more than 30 and it will be less than 500. So, here these both these viscous stresses as well as the turbulent effects both are important in this region, that is when you are going for the y plus value more than 30. Now, in this case the shear stress tau slowly will be varying with the distance from the wall, and within the inner region it will be assumed that so what you see this y plus for this value y plus between 30 and 500. So, you are assuming these shear stress to be constant and equal to the wall shear stress in that thin region, and in that basically what you see you get this u plus value, you will be getting the 1 by k of ln y plus b. So, this is what you see what you get in the case of the that region which is outside the viscous sublayer. So, here the shear stress tau will be varying slowly with distance from the wall, and in the inner region it will be assumed to be constant, and that will be equal to the wall shear stress. And regarding the length of the turbulence mixing, mixing length here this Lm, that is taken as the ky. So, see this u plus. So, you will have the relationship between u plus and v plus in terms of this k, that is so this will be 1 by k ln y plus b, and we also take it as 1 by k of kappa, that is E y plus. We are taking another constant. So, we call it as the 1 by k of ln E y plus. So, basically because this is a logarithmic function, in that u plus and y plus is varying in a logarithmic manner, that is why we call it as a log law layer. And in this case what has been found, people have done the experiments, and the numerical value of this kappa, that value is taken to be about 0.4, and b is taken out to be 5.5, or even E is taken as 9.8. So, basically this is known as the von Karman constant, and this von Karman constant is basically 0.54, and your this constant b, it is 5.5, or you can have E value as 9.8 for smooth walls. And once you have the rough walls, so you will have the decrease in the value of b. So, your u plus will decrease for the rough walls. So, your b will be decreasing, and because of these relationship, we call it as the log law in this case. So, that is why it is known as the log law layer, because of this logarithmic function which is seen here. Now, we will come to another layer that will be your outer layer. So, if you go to the outer layer, so the log law layer that is shown to be valid experimentally in the region. So, log law will be valid in region So, y by delta, so that value has to be more than 0.02 and less than 0.2. Now, for the larger value of the y, the velocity defect law which we have got, that gives you the correct form, and in the overlap region basically you have the log law and the velocity defect law, that has to be equal. So, based on that you can have the relationship, and the researcher Tannekes and Lumley, so they have shown that there will be a matched overlap in that So, you will have that function. So, by overlapping, if you make it equal, so you will have u max minus u by u tau. So, that will be basically equated to this log. So, that will be 1 by Karman constant kappa, then you will have ln of y by delta and plus a. So, that is basically applicable for the outer layer, and here the a is constant. Now, the thing is that this law, this is the velocity defect law only, and this law is many a times also called as the law of the wake. So, there has been close findings by the researchers, especially the Schlisting was one of the researcher who has done large amount of work in the area of, he has a standard book also on the boundary layer theory by Schlisting. So, that we refer also. So, in that so they have found that you have basically the if you go try to have the velocity profile. So, what you see that if you try to have this velocity profile, and you have u plus and you have log of y plus. So, what you see you will have, so this is your linear profile, and your profile looks is going like this. So, in this case you have u plus is y plus. So, that is this region, and then otherwise you have here this region is u plus is 1 by kappa of e y plus. So, this is your log law layer where this logarithmic relationship holds good, and so these are different points which are coming, and it has been found to be here correct. So, you will have this region as the log law layer. So, where this log rule holds good in this case. So, what we see that the turbulent boundary layer adjacent to the solid surface is composed of two regions. You have the inner region, which is 10 to 20% of total thickness of the wall layer, and the shear stress will be almost constant, equal to wall shear stress. That is what we have seen. Outer region will be where it is the law of the wake layer. So, there you will have the inertia dominated core flow from the wall, and it will be free from the direct viscous effects. So, when you go from the wall away, you will have inertia effects getting more and more dominated. Then if you go to boundary layer near the solid walls, the inner layer will have 3 zones. So, you will have linear sublayer where the viscous stresses will be dominating the flow adjacent to the surface, because there, because of the wall also the flow becomes 0. So, there the viscous stress is dominating. You have a buffer layer where viscous and turbulent stresses are of similar magnitude, and then you have a log law layer where the turbulent stresses dominate. So, so these are so that basically, now why we have studied this, because they will be used when we go and solve the Tandis flow, when we talk about the flow near the walls. So, how you have to model how these quantities are to be computed, how the depending upon the y plus value, how you have to take the different wall functions. So, these things are basically very important to be understood, that in which region which way these u plus and y plus is varying, and what are the functions, and accordingly you can have the calculation of the wall shear stress and then other related components that can be calculated in the case of any such kind of turbulent flows, which will be normally for the flat plate near representing the flat plate boundary layer, or even other kind of flows in the industrial applications. Thank you very much.